equation. Which is say is a map from tensor cube of a vector space to itself, an invertible map. Such that we have a nonlinear identity, which is which generalizes Yang-Baxter. So I have some mnemonic rules. So we write R1 to 3, and then we spread 1 to 3 to 3 other R's, and then we add the 2 more indices 4, 5, and spread them out like this, and add a 6 space like this, and then we write them in the opposite order. One, two, three. This is V. V is a vector space. Maybe finite dimensional, maybe infinite dimensional. Here we don't specify this. Typically, in interesting cases, it will be infinite dimensional. And another thing is the set theoretical version of it. The theoretical form. So it looks like the one written here. Let me put it TE. But V is replaced by a set X, and Cartesian product. Product replaces tensor product. Okay, in here. So and then otherwise it is a same equation. And more generally, maybe one can just speak about symmetric monoidal category. Symmetric. But at least in the standard context is the symmetric monoidal category of vector spaces with tensor product. In the set theoretical context is the symmetric monoidal category of sets and maps. Symmetric, which means that we can permute the components in the product space. So this is the first equation we are interested in, and the second equation will be a local Yang-Baxter relation, and I call it Maillet-Nijhoff local Yang-Baxter equation. Local Yang-Baxter equation, but more concretely, I will be talking about its spatial form, which I call Korepanov's form. And Korepanov forms corresponds to the symmetric monoidal category of vector spaces, but instead of tensor product, we use direct sum operation. Okay, so and let me write it explicitly. So how it looks like. So let me use letter L. So roughly speaking, we write the Yang-Baxter equation, but with some arguments. L1, 2, 1, 3, G2, L2, 3, G3 equal L2, 3, Z3 prime, L1, 3, G2 prime, L1, 2, G1 prime. So let me use just identification of this equation, if I will be referring to it later on. And what is what in this equation? So first of all, GIs are just 2 by 2 matrices. GIs are like AI, BI, CI, DI in GL2 group. over complex numbers, maybe over real numbers. But as soon as we stay algebraic, we don't care what kind of numbers we take, any field. And likewise for GI primes. Okay, so everything with primes. And then L12 is a direct sum analog of L12 in the tensor product case. And maybe it's the simplest way to explain it, just to write it out explicit form. So the equation is written in the direct sum of 3 copies of the real numbers, for example, if our base field is, and we write A, B, C, D. So G is A, B, C, D, 2 by 2 matrix. And then L12 of G is, we write 1 block A, B, C, D, and then we complete it to 3 by 3 matrix by adding zeros and ones like this. And likewise for L13, which is, we put matrix A, B, C, D as at places 1 and 3 in 3 by 3 matrix. So it will be A, B, C, D like this, and then we fill up the rest by zeros and 1 on the diagonal. And L23 is of G is 1, 0, 0, 0, 0, A, B, C, D. And so we consider this as an equation for 6 matrices given by GIs and GI primes. So unknowns. Unknowns are G1, G2, G3, G1 prime, G2 prime, G3 prime. And so we just multiply matrices, equate. So we have nine scalar equations on how many? 4 times 6 on 24 variables. So we have considerably smaller number of equations. So we have plenty of free degrees of freedom. And the reason to be interested in this equation is that it is related to tetrahedron equation, and the relation goes as follows. So, relation of local Yang-Baxter relation to tetrahedral equation. So what we do is the following. So let S be a subset of the group GL2 power 6. Okay, we have 6 unknown matrices, and so this is why we take a 6 power in the group, and we are looking for a subset of the 6 power in the form so be a set of solutions of the local Yang-Baxter equation, but not just an arbitrary subset of solutions, but in the form of a graph of a map, in the form of a graph of a map from R, say, Y to Y cube to Y cube. So, which means that so S is equal as a graph of a map, which is by definition looks like this: a set of pairs where G lives in the Cartesian cube of a set, and Y is a subset of GL2. So kind of formalization of the special class of solutions of the local Yang-Baxter equation. If we manage to find such a subset of solutions, then it is expected that R will solve set theoretical tetrahedron equation as a map from the cube of Y to itself.
Renat, am I right that this condition is equivalent somehow to the uniqueness of the solution? Uniqueness.
No. Here, no. I don't specify. I don't talk about uniqueness. Even I don't claim that the R will be solution of the tetrahedron equation. Just what I say that if we find such set of solutions, then we can hope, we can expect that it will be solution. But for the moment, I don't talk about uniqueness. But you are right. So in some uniqueness somehow will make sure, almost make sure that it will solve tetrahedron equation. But on this level, we are just trying to identify a set of solutions in the form of a graph. Then of course, there is a work of checking if tetrahedron equation is satisfied, but no uniqueness at the moment.
Excuse me, can I also ask a question, please?
Yes, please.
So in practice, it is true that any solution that comes as unique solution of this matrix three-factorization problem, it is indeed a solution of the tetrahedron equation. If it's not unique, it may not be. You can choose any sub variety which is not a solution. However, my question is the following: in the case of the Yang-Baxter equation, it is very clear which solutions, even the unique ones, are indeed solutions to the Yang-Baxter equation. So you have a matrix refactorization problem. It gives you a unique solution, and this is a solution of the Yang-Baxter equation if you go to put three matrices in a row, and the matrix refactorization gives you the trivial solution. Is there any analog here? So is there any condition under which we can verify that the solution that comes as unique solution of the matrix refactorization indeed satisfies the tetrahedron equation?
No, I don't know. As far as I know, and in my experience, so typically we just identify some solution in the form of a graph, and then we just check by substitution if tetrahedron equation is satisfied. But I agree that presumably there is a formal argument based on some non-degeneracy or uniqueness, as you call, which would allow to conclude the tetrahedron equation without calculation. But typically one is interested in some concrete solutions, and then usually what I do myself, I just pick up the map and then go to Mathematica to see if it is verified.
Yeah, thank you.
You're welcome. Now let me be concrete. So first of all, let me make a first remark. So if dimension of Y, so Y kind of we look at as a submanifold of GL2. So if we are looking for one-dimensional, so the simplest possibility, then there is a classification result. By Sergeev, which dates quite a long time ago, something like 1998, I think. And let me just give one single example, maybe relatively interesting example. Example 1. So y is given by x 1 1 0. We restrict to real numbers here, and even more strictly positive real numbers. So here I'm very specific. So the claim is that then with this y, so the strictly positive half real axis, we have a solution, and it is called Hirota map, which is given by R. So instead of G1, G2, G3, I just write X, X1, X2, X3 is given by X1, X2 divided by X1 plus X3, X1 plus X3, X2, X3 divided by X1 plus X3. And yeah, so actually you have a uniqueness in this case. So if you just pick up this y and substitute into the local Yang-Baxter relation, then you will get just 3 independent equations, which give exactly this solution. And you see that, for example, if you try to make it over all reals, then you encounter already some problems of singularity, division by 0, for example, if x1 plus x3 vanishes. So it is a kind of delicate thing of identification of the subset Y to have a true graph of a map. And for example, if you enlarge, for example, if you replace your basis field by some other field, complex numbers, for example, then you don't have already a set theoretical map in strict sense because of the singularity. I mean, in the set of complex numbers, it is not evident if you are able to cut out a subset of complex numbers where this will be a true map, which relates the same, I mean, which identifies the cube of this subset to itself, I mean, in one-to-one manner. But real number, strictly positive real numbers are kind of rare cases where this becomes a true map, as here. And actually, from the viewpoint of cluster algebras, so this is a manifestation of the positivity in the cluster algebra setting, that these positive reals indeed are distinguished from that standpoint. And maybe here I can remark that I have a recent result on generalization of this Hirota map to fully non-commutative case. Fully non-commutative case. A result obtained, at least it is published last year in collaboration with Adam Doliva. So what is it? So of course we go out from this setting. So what we do, we just try to use the same formula, but without assuming that x1, x2, x3 commute between themselves. And this is indeed possible. So we obtain, but we have to somehow order the terms here. So x, so R1 x1, x2, x3. So I just rewrite this formula, but reordering terms, x1 plus x3 minus 1, x1, x2, x1 plus x3, x1 plus x3 inverse, x3, x1, x2, sorry. So here you can assume that y is not just positive real half axis, but any set where you have a commutative addition. Even zero, you don't assume that zero is there, so it is not a group, additive group, just commutative semi-group, and with associative multiplication, but you don't assume that the multiplication is commutative. And then it is a matter of check by hand that if you use this substitution, then to verify the tetrahedron equation, you don't need commutativity. You just accurately keep calculating, collecting common terms, extracting some inverses, and everything in the end cancel out, and you will get a true solution of the tetrahedron equation.
Rinat, do you have some explanation? Is it related to quantum groups or something else?
No, it is quantum groups. After all, it is a quantization in like we do in quantum mechanics. You have a deformation parameter, and then when you send deformation parameter, so you need a symplectic structure which is consistent with a map, and then you can quantize by replacing your Poisson algebra by non-commutative algebra, like in the deformation quantization. And then you will get a solution in that algebra. But here, nothing like this. So we don't have symplectic structure, no quantization. We just declare that the variables we are dealing with are just some non-commutative objects.
Just a free non-commutative algebra?
Yeah.
Or quantum Tarai?
No, nothing. You just associativity, nothing else. So it can be free, it can be not very free, you can have relations, but let me just give you example. So example of example, okay? So example one, say. Let us take Y to be a matrix Xij for ij from 1 to m. Okay, but with Xij to be real numbers. But first, I assume that Xij's form upper triangular matrix, which means that if I strictly greater than j, then Xij is 0. Okay, and the second condition, the diagonal is strictly positive. Okay, so my set Y is like this. And now what happens? So first of all, I can add such matrices to each other. So if on the diagonals I had strictly positive numbers, then after adding them, diagonal keeps staying strictly positive. And the second thing, all such matrices are invertible because I have to invert the diagonal elements. And then the inversion of the triangular matrices doesn't need any invertibility of extra invertibility of elements, right? So I have an algebraic object of such matrices where I have these two operations. And now I can just plug this Y into this formula, and everything makes perfect sense. So the claim is that I will have a solution of the tetrahedron equation on the set of such matrices, which is pretty nice because we have a high dimensional Y we can study, I don't know, like maybe symplectic structures which are compatible, whatever. I don't know. This is a completely unexplored domain, I would say.
Can I ask a question on this
Yes.
example, please? I see this map that you wrote, this Hiroto map, is involutive. I mean, in the sense that the map composition with itself, its identity.
Right.
I also see, if I'm not mistaken, the non-commutative one, since you wrote x3 times x2 is also involutive.
No, I don't think so, because it will be involutive in commutative case, that's true, but the inverse R will look like, I mean, the inversion will be multiplied by from the right.
Mm-hmm.
And so for this reason, I think this is not involutive.
Mm-hmm.
But I never asked myself this question. So, but I would say from from first sight, I would say that this will not be involutive.
Okay, thank you.
You're welcome.
May I ask a question
Yes.
about setup? So why you so much care about zeros and poles, etc.? If you just have a complex setup and we admit some poles, and is it really make any sense to have, you know, is it really important to keep a regular map?
Yeah, this is a very good question. And in principle, so if you are interested just algebraically, I would say that it doesn't matter too much. But from the point of view, I'm a quantum person. So you usually in my research work, so what I do, I have some set theoretical stuff. Then I'm looking for some symplectic structure, and then I quantize. And in this case, I think this really matters if your map is globally well defined or not. Because you know, when you quantize, so your variables becomes operators, typically self-adjoint operators. If they were positive, then they become positive self-adjoint operators. And then the singularities really make things bad on the quantum level. For example, your operator will not be self-adjoint, for example. Then you will be facing the issue of self-adjoint extension. So somehow quantization will not go as smoothly as it would when everything is globally well defined.
Thank you.
Sorry, Renato, may I also ask a question? You definitely played with these formulas. Maybe you will talk about this later. But if we proceed with repetition of this procedure, so if we make it multiple times, what we actually is there some structures revealed? I mean,
which structure you mean? You want to
I mean something like we observe in cluster algebras like this. It's not Laurent. It's obviously not Laurent from this from what you wrote, but maybe, well, we know some examples, for instance, when this miraculously these structures become periodic at some key in some cases, and so on. So you probably had some experiments and you probably know the answer.
No, I don't. And actually, as I said in the beginning, so I don't didn't work much with in particular tetrahedron equation in last years, but because of collaboration of Adam, we had some activity last year, and then on preparing this talk, I got interested back with Bazhanov-Mangazeev-Sergeev solution, but not more than that, because you know the subject is enormous, and actually I don't know. You have to be very much motivated to try anything. I mean, you want, if you want something specific, then you will do that. But I didn't have such motivation. But but this example, indeed, it is very much closely related to cluster algebras, and this.
So I'm just eager to know about this n by n case. So yes, that's.
Yeah, no, n by n case. It is just for illustration. I mean, I never work it out any further. So even this non-commutative case myself, I did know it for a long time that it exists, but somehow even I have some papers about non-commutative Liouville equation and so on based on such kind of non-commutativity, but it is not clear what to do with such things because you know, at least when you quantize by deformation, you have just one single parameter as to control. But already quantum theory is not easy thing, you know. But here is a fully non-commutative, and
But did you probe something against like this pentagram maps?
Yeah, I played with fully non-commutative pentagon, if you mean this, because yes, pentagram, I think, is a dynamical map, which is not a pentagon equation. But maybe if you mean by pentagon, then with pentagon equation, I have some experience, also on non-commutative case. But as far as I remember, there is an integrable system given by pentagram map, which is different.
Yes, yes. And also it might be fully non-commutative also.
This you know, right? This is a statement.
This is a statement. Yes.
I see. Yeah, there are many cases of discrete integrable equations which are generalized to non-commutativity. I agree. And on the level of say Yang-Baxter or tetrahedron, this is indeed is reflected in the existence of such non-commutative versions of equations.
Rinat, but is it involutive, this non-commutative map?
Yeah, I think it is not.
Actually, it's not. I just checked.
You checked? Yeah, I see. Thank you. Yeah. Because I remember that the inverse of this map, if you try to calculate it, you will have to multiply from the right by inverse of the sum.
There is another analogy. The Hirota map is the same as the Liouville solution, which is related to the unipotent group. So in this example, the parameter and the group are the same. So
but you see, what you say applies only in commutative case, right? In the group Lie group theory context, these are coordinates or parameterization of the groups. Mm-hmm. So nobody never discussed, I think, a non-commutative version of this map.
Thank you. Very interesting example.
Okay, now that ends my say introductory part. But I'm talking already for more than half an hour. So. But let me now change to more specific example. So let me put it example 2, and the rest of my talk I will talk about this example and elaborate on that. And actually, it's my favorite example and a solution which always fascinated me enormously. So this is a geometric solution of Bazhanov-Mangazeev-Sergeev. Bazhanov-Mangazeev-Sergeev geometric solution. I think this is something like 2008. What is it? So, but strictly speaking, I'm not sure that this is a solution in the sense I defined it today, right? As a graph of a truly well-defined map. So I think it is almost well-defined map, but probably with some singularities. Let us see. So let me just explain it. What is it? So Y, let me put it, Y may be contained in the set I'm going to describe. So it is a 2 by 2 matrix, real valued, given by coefficient sine of gamma, sine of delta plus beta, sine of delta plus gamma, sine of beta, and everything is divided by sine of delta. And here I have a beta, gamma, delta, say real numbers on the interval between 0 and pi. And additionally, beta plus gamma plus delta is less than pi. So ideally, we would like to define Y to be this set. But let me describe you how the solution looks like, and there is no need actually to check that it is a solution because it is purely geometric and it comes out just by as a geometry fact. So first of all, I will draw these variables as angles of a quadrilateral. So let me draw a quadrilateral, generic quadrilateral. And I put, I want it to be oriented, and I will orient it with two coordinate axes. And I put 4 numbers to 4 corners. So alpha, angle here. So think of Euclidean quadrilateral with straight sides and so on. Beta I put here, I put gamma here, I put delta here. And as we know, alpha plus beta plus gamma plus delta equal 2 pi, right? Because if we draw a diagonal, then we will get 2 triangles whose angles sum up to pi. So we have 2 triangles, so all angles sum up to 2 pi. So this is why alpha is not here. So I keep only beta, gamma, delta. But of course, to be able to define, so here is a mistake. So it should be less than 2 pi, right? So this inequality, we need just to be able to define alpha as a 2 pi minus the other angles. And so then, at least at this level, so we can think of Y as a set, because whenever we pick up some triple of numbers in this interval satisfying this, we will be able to define a quadrilateral, geometric quadrilateral. But now what we do next? So first of all, this quadrilateral is defined up to overall scaling. And actually, I define it up to scaling in 2 directions. So what I mean? So let me pick up a first quadrilateral. I pick up first quadrilateral with angles delta 1, alpha 1, gamma 1, beta 1, but I fix this side to be of length 1, and this side to be of length 1. And then, so I just draw it on the plane. And then I pick up second quadrilateral with a quadruple of angles alpha 2, beta 2, gamma 2, delta 2, and attach it along this side. So this side is common, and I just draw it like this. And here I have some arbitrarily chosen beta 2, delta 2, alpha 2, and gamma 2. But I do this in space, right? And additionally, I fix this side still to be of length 1. So given the angles, of course, I can adjust the lengths and draw such a thing. But I want to do this now in space. So I don't want this to be in the plane. So which means that I can rotate rotate around this axis, this second quadrilateral in the space. Okay, this is a freedom, which we don't fix yet. But on the level of lengths, everything is fixed, because if these two lengths are given, then these angles are given, then these lengths are determined uniquely. For example, this length is fixed, this length is fixed, as well as this length is fixed. And now what I want to do, I want to attach the third quadrilateral with its angles. And but I can complete it into a piecewise linear surface like this. So alpha 3, beta 3, delta 3, gamma 3. And to do so, I will use this freedom of bending this situation to be able to adjust these two sides and these two sides. Okay, this fixes the length, but the angles are not affected by changing the length, right? So we get this kind of space embedded into space, piecewise flat polyhedral surface, right? So this is the first configuration, and here I need some generic position now. What I want is that this surface, I want it to be flat. Namely, the dihedral angle, I don't want that the dihedral angle along this edge, I don't want it to be 180 degrees. So I want it to be strictly less than 180 degrees. Likewise for these dihedral angles, and likewise for this dihedral angle. So I want it to be really in a volumic structure. And then what happens? Then I just draw. So you see, you have these 3 points which are not aligned along one line, right? So then we have a unique plane which passes through these 3 points. And we have unique plane which passes through these lines as soon as they are not aligned along one line. And one more plane which passes through these lines. And then these three planes will intersect at one common point, right? Backside of the picture. So there will be something like this as an intersection point. So this point will be uniquely determined. And then what happens? So for primed angles, you just read out the angles of the 3 quadrilaterals which I created on the backside of the picture. And that's a map. That's a map. So let me try to, I don't know, copy this picture. And erase all these angles, everything I drawn so far, and then I just identify newly created angles like delta 2 prime, gamma 2 prime, alpha 2 prime, beta 2 prime. Here we have beta 3 prime, alpha 3 prime, gamma 3 prime, and delta 3 prime, and this angle will be delta 1 prime, beta 1 prime, alpha 1 prime, and gamma 1 prime. So the remarkable fact that alpha I, beta I, gamma I, delta I, for I from 1 to 3, mapping to alpha I prime, beta I prime, gamma I prime, delta I prime, I from 1 to 3 solves. So this is a Bazhanov-Mangazeev-Sergeev. They say that it solves tetrahedron equation. which personally I find an amazing fact, because just very existence of Euclidean geometry gives us a solution. But as I said, strictly speaking, we have some generic position condition that these 3 points which determine three triples of points which determine the intersecting planes exist and uniquely defined. Otherwise, geometric argument doesn't work. And in principle, you can imagine the choice of the initial configuration where, for example, everything will be planar, right? Then you will not have a uniquely defined triple intersection point and so on.
Could you please explain? Could you please explain what this geometric picture have to do with this matrix that you write in the curly brackets? You have a matrix here,
yeah,
right?
Because you just think of this matrix as a so you see we have matrices here, and each matrix acts on columns of height 2. And now I want to associate to this 3 by 3 matrix acting on column 1, 1, 1. So these 3 lengths, these three ones is the initial column 1, 1, 1. And then I take these matrices, multiply them like in local Yang-Baxter equation, like here. And then I apply it to this 1, 1 column, and the result will be the 3 lengths here. A, B, C. So this map is mapped to A, B, C. Of course, which are defined by these quadruples of angles. Now we erase this front side of this polyhedron, which is a kind of deformed cube. And of course, the configuration 1, 1, 1 stays intact because we keep this boundary, and this ABC as well, right? They will be the same, which means but the matrix now is composed differently from different blocks here. This is one matrix, another one, another one. So but if you multiply them, so let me draw this auxiliary dashed lines to visualize it better. Like maybe I change the color, like repetitive lines if you want. And here it will be so this should be blue now. Okay, so these blue lines play the same role as here for identification of the quadrilaterals in uniquely oriented fashion. And then the multiplication in the local Yang-Baxter equation of 2 by 2 matrices corresponds just to composition of them according to this picture. And then just the effect of this action of matrices corresponds to calculating 2 lengths of the quadrilateral starting from the given length of 2 other sides. Okay, have I answered your question?
Yeah.
Okay, thank you. And this also makes it clear why this just geometric identification of angles solves the local Yang-Baxter equation, simply because 2 matrices act in the same manner. But of course, instead of ones, you can pick up any triple of lengths. and the same conclusion will be verified. Okay, now that's a remarkable solution, which doesn't need any calculation, actually, just the geometry makes sure that it is a solution. But then another remarkable fact is that there is a reduction of the solution to so-called circular case. Circular case, which means that you just draw a circle, and you require that your quadrilaterals are not arbitrary quadrilaterals, but inscribable into a circle, which means that if you have angles beta, alpha, gamma, delta, then now you have extra condition that the opposite angles sum up to pi, right? Alpha plus delta equal pi, and beta plus gamma add up to pi. Just a geometry fact. And now from 3-parameter solution, so your Y space, if you want, was 3-dimensional. And now if you impose the circular case, then you reduce the dimension of your reduced Y to 2 dimensions, say alpha and beta. And but why solution survives? Due to another beautiful geometrical theorem, I think it is called Miguel theorem. Miguel theorem implies tetrahedron equation, which means that if you start from circular quadrilaterals, then the newly created quadrilateral still will be circular, because this configuration will be inscribable into a sphere. And by Miguel theorem, this intersection point will find itself on the same sphere. So again, you don't need any calculation to check that you have still a solution of the tetrahedron equation. So the amazing manifestation of the power of geometry. I never seen anything like this before in my life. Okay, and but even more, Bazhanov-Mangazeev-Sergeev, they observe that there is a compatible symplectic structure. There is so Bazhanov-Mangazeev-Sergeev say that there is a compatible symplectic structure, which is given by a very simple fact. So I mean, let us pick up 2 independent variables, say alpha and beta, and then we have d alpha I, which d beta I, sum over I from 1 to 3, this is for the left hand side, is equal sum for I from 1 to 3, d alpha I prime with d beta I prime. And this is a key thing for going quantum, and not in the sense I talked about before when I just talked about freely non-commutative. No, here we have a manifold and symplectic structure, and actually the absence of singularities, I believe, matters here. But here, when Bazhanov-Mangazeev-Sergeev never discussed this issue of singularity, they just went purely algebraically, ignoring these kind of issues. And as soon as the quantum theory was well defined, they didn't care what happened before. And but somehow, I think that they knew that somehow this reality conditions on the angles is incompatible with what they did on the level of quantum theory. For example, I'm using the annotation. They write this G like K A star minus A K, where K is a sine beta divided by sine alpha. A star is a sine of alpha minus beta divided by sine of alpha, and A is equal sine of alpha plus beta divided by sine of alpha. And so if you write A star, so then you pretend probably that this should be some kind of conjugation, right? But clearly we are far from being these two fractions to be conjugate of each other, unless that you say that beta is pure imaginary. Then it makes sense. But then the angles you cannot treat in the same manner, so somehow you get problems. But otherwise, yeah, and just maybe I finish here the description. So first of all, you can observe that G is actually SL2 matrix, SL2R, and additionally K squared plus A times A star is 1. This is the actual determinant of it, right? So this is equivalent. And this is true. So the matrices are SL2 matrices. And say in an open dense subset of alpha beta space, I mean, so alpha beta I would say should be in the unit interval of length pi, and maybe this is only condition. So on this square of side pi, so you have a solution defined almost everywhere. But I never analyzed, but at least you see, when you have these conditions, you don't have any problems of division because sign stays strictly positive. But on the level of transformation to primed variables, I'm not sure. Somehow geometry encounters some degeneracy cases. But anyway, you can go. I can stop any moment. So tell me, please, when how much time I have.
Rinat, I think you have time. 30 minutes.
So is it normal
like.
in this seminar so that we go that far?
Yes, half an hour. If you
okay, but like. Anyway, let me then tell you what I plan to tell, because I haven't finished yet what I wanted, and then I stop. Maybe this will require much less time than half an hour. So let me first remark that Bazhanov-Sergeev had another paper where they had something more general. So so let me put it as a remark. So this is a special case. Let me call it a constant case of a more general solution. Which is a spectral parameter dependent. Of Bazhanov-Sergeev. And I think it is 2006. And the form of the solution is like this: G equal lambda k y minus lambda mu x and mu k. And again, so k squared is equal 1 minus xy. So if you want, y plays the role of a star. here, sorry, A star is analog of Y, and X is analog of A. Minus, you see it clearly. So if you put mu equal lambda equal 1, then you get back to this. But actually, in the map, so you have so they impose. So this is not a result of solution of the local Yang-Baxter equation. They impose the conditions that lambda prime is equal lambda, I mean i's, and the mu I primes equal mu I. So I would say that this is a solution found by ansatz. If we come back to Dima's question in the beginning about uniqueness. So it is an example of a non-uniqueness, because if you try to solve the local Yang-Baxter equation in full generality without imposing any conditions, then you will have at least 3 degrees of degrees of freedom. So just on the level of map, you will have a free parameters, completely unfixed. And but this is kind of free, I mean unrestricted case. You see, you have a y one variable, x is second variable, lambda third variable, mu fourth variable. So you have 4 degrees of freedom, arbitrary. And so if you try to solve, you will end up with some free parameters in the end. But for some intuitive reason, Bazhanov-Sergeev just say, let us consider some system of equations on top of the local Yang-Baxter equation, impose these extra conditions. And they come up with a solution. I will not write the prime variables, they are pretty complicated. But you can check, say, on Mathematica that what they obtain solves the tetrahedron equation. And now what they do? So they take into account this compatible symplectic structure, and then they go quantum. So they quantize it just purely algebraically, ignoring all the positivity or reality conditions. So quantization, they identify the Q oscillators. So what is Q oscillator? It is this kind of thing. So let me put hats. These are now operators. Say in deformation quantization, for example, A star equal Q minus 1. And we have K squared is Q1 minus A star A equal Q minus 1, 1 minus A star. So you see the difference here. I write A star A, but here I write A star. So this is fully, I mean, a completely non-commutative context. So you should be careful with all orderings. And what else? So K, if you want, you can think of just this algebra. This algebra, then this defines element K. But you see, it is required that K to be invertible. Then you see that you have to avoid when A star A equal to 1. But if it is not equal to 1 and Q is a real deformation parameter, then you can define K as an operator square root of the right-hand side and so on. But anyway, this algebra implies that the K commutes with A star like Q A star K, and the KA commutes like Q minus 1 AK. So this is the Q oscillator algebra, and here is this essential thing to assume that Q lives strictly between 0 and 1. And then they pick up a Fock representation. which means that you look for a vector which annihilated by A, and then you assume that it is normalized to 1. But if you look at the paper, I'm just following it now, reviewing the paper, but they ignore all these Hilbert space aspects of the representation. They go just algebraically. For example, they even don't mention about normalization like this. But for me, it will be important. Then they will be normalized orthonormal basis, which is A star and acting on this vacuum divided by Q squared n square root. So so this is a Q. Let me x. And this is a product 1 minus x squared to 1 minus xn. Okay, so I'm using this kind of Q factorial notation. And in particular, K will be acting as a diagonal matrix, which is given by Q power n plus 1/2. You know, if you're familiar with the harmonic oscillator, so then even 1/2 shows up naturally in this context. And this is very nice representation. And so the main result of Bazhanov-Mangazeev-Sergeev is that they managed to calculate quantum R matrix, which solves quantum tetrahedron equation. So quantum solution of the tetrahedron equation, which is roughly speaking goes as follows. So first of all, you look for a known operator which conjugates all AI's to AI primes. The AI primes are calculated from the local Yang-Baxter. Okay, so they are explicit expressions. And then this is if you want a linear equation for unknown operator. And likewise for A stars. So I mean these should be hats prime. Okay, so and RKI R minus 1 KI prime. And but now additionally we require that the triple vacuum, because we are in triple space, stays invariant. Then you can easily calculate actually this R matrix, because we just need to act to arbitrary basis element in the triple tensor product. But then, given the fact that they are obtained by acting by creation operators, so we have this R acting on A1 star hat power n1, A3 hat power n3, right, divided by Q squared n1, etc. square root, right? But now you can use this conjugation formulas to pull this R to the right, and then you will put primes on this side, and then use this last equation to absorb this R by the invariance of this vacuum. So the result will be A1 star hat prime n1, A3 star prime n3 divided by Q squared n1 vacuum. And now we have done, we managed to calculate this R matrix, because now it suffices to apply from the left hand side M1, M2, M3 from the right, M1, M2, M3, and then you end up with vacuum expectation value of A1 power M1, A2, M2, A2, M3 with hats, normalized, same with primes, N1, N2, N3, right? And the vacuum expectation value. I don't write, I mean you write this. And prime operators are explicit expressions in terms of non-prime expressions, and then you pull all annihilation operators to the right, and so it is clear that you can calculate this matrix element in closed form, as Bazhanov-Mangazeev-Sergeev do, and they end up with pretty nice formula in terms of Q hypergeometric series phi to 1. And what I'm talking about all this because I have a message to add to this picture. So my message is the following. So the claim. My message, a message of today. Operator R is unitary. Is unitary in the Hilbert space. L2 of Z positive power 3. So we have a Hilbert space of sequences, right? Because our Fock space has an orthonormal basis indexed by positive integers. So that means that the elements of this Hilbert space are coefficients, expansion coefficients with respect to this orthonormal basis. And so it is identified as a Hilbert space of square summable sequences. And my message is that there is a reason, it's not theorem because I didn't work out all the details, but there is a reason I have an argument to justify that this R matrix is actually a unitary operator in the space, which in particular implies that the inverse of it, you don't need to invert this map. You just complex conjugate and exchange the arguments, as we do in the Hermitian conjugation, right? It is a transposition accompanied with complex conjugation, and this will be the inverse of this R matrix. And to finish, let me give you why I made this claim. Why this operator is unitary and something which is completely ignored by discoverers of this R matrix. So my claim the message is based message is based on the following. So first of all, so I take SL2R group, which is equivalent to SU11. So what is SU11? It is a group of matrices, of complex matrices A, B, but here bar means complex conjugate for me, okay? And then SU11 is a group like this. Absolute value A squared minus B absolute value squared is 1. A, B are just complex numbers. So this is a subgroup of GL2C, actually SL2C, because this is just a condition that the determinant is 1, right? So this is why S, but it is not SU2. It is not unitary, but you see, with unitary we would put minus here, but there is no minus, so it is kind of hyperbolic version of the unitary, and the relation between the two is very simple. It's very simple. So if you take SL to R, element of G, then you map it to conjugate of this form 1 minus I, 1 I. G 1 minus I, 1 I inverse. So if you take into account the action by isometries of in the upper half space with hyperbolic metric, then this just corresponds to relating upper half space to the unit interior of the unit disk into the unit disk model of Poincare upper half space. Okay, this is the first point, and the second point, and so this lives in SU11. Okay, so we have a group manifold of SL2R. And the second point is that I pick up, I identify this SU11 with Y. So Y is a common notation for my set theoretical solution, right? So this will be SU11 is my Y, which sits inside a unitary group of 2 by 2 matrices. Unitary, but not as a subgroup, not a subgroup. And the map is the following. So if I have A, B bar, A bar, then I map it to G, which is a 1 over A, 1 B bar minus B, 1. So just is a matter of exercise that checking that this is unitary matrix here, unitary 2 by 2 matrix. And the division by A is perfectly legitimate because from here you see that absolute value of A is strictly greater or equal to 1. So A in the subgroup is never 0. So we can define divide by. And the third point, maybe I put that SU11 is equivalent to unit complex circle times complex plane. So T is Z in C, Z absolute value is 1. Okay, and the relation is very simple. It's very simple. Since A is not 0, it means that A divided by its absolute value lives in unit circle, right? So if I put, define it by Xi, then G is parameterized by 1 plus B absolute value square root times Xi B bar and 1 plus B absolute value squared Xi bar, right? So my matrix is completely parameterized as a pair of complex number on the unit circle and just an arbitrary complex number B. So as a manifold, so this is a pretty nice object, right? Complex planes and unit circle. And then here is a theorem which justifies my claim about unitarity. So let S be the set of all solutions of local Yang-Baxter equation, where Gi primes sit in Y, okay, as a subset of unitary 2 by 2 matrix. Then S consists of two connected components, where each of them is a graph. S plus minus is a graph of certain maps R plus and minus for some invertible maps R plus minus, which but this time, so the important point here, no singularities whatsoever. This is well-defined map, which is not analytic because you see there are some absolute values, but otherwise it is a smooth, well-defined map from Y cube to Y cube, which is essentially the group manifold of the group SL2R. And even more, the A star in the Bazhanov-Mangazeev-Sergeev formula becomes the complex conjugate of A. So it is a true analytic. I mean, you have a star structure compatible with the map, and then maybe final thing I say. So the compatible symplectic structure, which is essentially the same as a symplectic structure on C. So dz wedge dz bar divided by 1 plus zz bar. This z refers to this b. I mean, in this identification as a product space. This T plays the role of spectral parameters in this map, which I don't mention. But now, instead of real symplectic structure between angles of quadrilaterals, you have a symplectic structure on the whole, which is actually Kähler symplectic structure, and you see it is nowhere singular, so this actually justifies that the quantization of Bazhanov-Mangazeev-Sergeev is a genuine quantization of this space. But when you do genuine quantization in that sense, then the corresponding symplectomorphism becomes a unitary transformation in the Hilbert space. Okay, I stop here. Thank you.
Thank you very much, Rinat. But what do you mean by genuine quantization?
Yeah, so this concerns the question of Alexander Mikhailov, I think, who was asking the question about why it is important to have a non-singular every-way defined maps. And when I talk about genuine quantization, I mean that we start from true symplectomorphism of every way well defined on the symplectic space. And then taking into account, say, that our space is a topologically trivial space. So C can be thought as a simplest two-dimensional symplectic space like PQ plane in quantum mechanics. So then we go quantum, and all the corresponding operators will be self-adjoint, or for example, the quantum version of Z will be A, and the conjugate, Hermitian conjugate in this Hilbert space of A will be quantization of A star in Bazhanov-Mangazeev and so on, but not quite the A's, but some other multiples of A's. I don't want to go into this part, but the message is that so when we go to complex matrices, then the Bazhanov-Mangazeev-Sergeev solution becomes a well-defined set theoretical solution, first of all, with well-defined symplectic structure, and the quantization becomes a genuine quantization, I mean, without cheating. So let me put it this way, because if you keep, on the level of deformation quantization, no problem. So you just keep things algebraic. But if you want to deal with Hilbert spaces and self-adjoint operators, unitary operators, you should be very careful, very careful. Just an example. Just take this quantum oscillator, Q quantum oscillator, and take in this quantization, of course, A star will be Hermitian conjugate of A. But then you can ask, how about this operator? Is it self-adjoint? And the answer is quite unexpected. It is self-adjoint when Q is inside the unit interval, like here. If Q satisfies this, then this is self-adjoint. But if Q outside the unit interval, like Q bigger than 1, then it is not self-adjoint. It is symmetric, but not self-adjoint. And there is a very sophisticated theory of self-adjoint extensions of it, which eventually boils down to non-uniqueness of the measure of the corresponding orthogonal polynomials defined by recurrence relations. So you know that there is a still TS theory of orthogonal polynomials. I mean, if you have some positivity condition on the coefficients in the recurrence relation, then there is a theorem, a deep theorem of existence of measure on the real line, which makes these polynomials orthogonal with respect to measure. But sometimes this measure is not unique. And then here we have exactly the case when if Q is like this, then the measure is unique. If Q is outside, then it is not unique.
Renat, am I right that on the algebraic level, the situation is very simple? So it is the most simple case, two-dimensional with the canonical symplectic structure. So algebraically, it quantizes trivially. But the
no. It's the answer is no, because just think of Bazhanov-Mangazeev-Sergeev solution. So if you try to make operators quantized angles to be self-adjoint real, then you have an issue. You have to the quantization certainly is not the one here, and it is not obvious. But I suspect that their modular symmetric quantization, they have another quantization. I admit probably that one the right quantization, but this has to be checked because they never discuss this issue of reality and so on. So what they do, they quantize it algebraically, but they have at least two different quantizations. And which one is which is the right one? It is open question.
Mm-hmm.
But here, what do they do with the quantum oscillators and the Fock space? They are quantizing some other space, which is the one which I tried to explain here, which is the SL2R group manifold. But it is not, it is three-dimensional, right? It can be symplectic, but I didn't say that this psi plays the role of spectral parameter, like in here. So the transformation is almost, they stay intact up to sign. So plus minus somehow affects them. And essentially the quantization part sits in the C plane, and then it is symplectic.
Mm-hmm. Thank you very much.
Renat, may I ask a question?
Yes.
This, usually this kind of Yang-Baxter maps we associate often, I would say, with dressing matrix or Darboux matrices for some integrable systems, differential difference systems, right? What about the matrices you playing with, and especially in the non-commutative case? Is there any association with these systems or dressing factors?
You of course, but at least if you quantize starting from some compatible symplectic structure, of course you are just quantizing the corresponding classical integrable system. That is clear to me at least. But again, going back to singularities, so you can study solutions of your integrable system, classical solutions, and if the associated, say, tetrahedral map has singularities, to me it means that you have to deal with singular solutions of classical equations. And this happens like in the Liouville equation, for example. And, people discuss, but not much about these singular solutions. But these singularities really pop out on that level.
No, I'm not talking now about singularities. Yeah. I'm talking about the examples you give to us, which are commutative and non-commutative, or this geometric example. Is it known that what kind of differential difference equation integrable correspond to that Lax representation, things like that? Or it's just you put, like you say, we write this ansatz, put an equation in this local Yang-Baxter equation and solve it and happy with that,
No, but the local Yang-Baxter equation, eventually it was invented on the basis of these discrete integrable systems behind of them. So actually what you do with local Yang-Baxter, you put now the arguments, these G's and G primes, as a function on the cubic lattice. On the cubic lattice, so these arguments becomes discrete variables sitting on the vertices of this lattice. And then you write this local Yang-Baxter as a local equation inside each cube. And so you have some number of components, like 4 variables for matrix coefficients, and then there will be some system of discrete equations for them because now they become functions on the vertices of this lattice. And this is a very general fact. So, and in particular, any solution of the local Yang-Baxter equation is related to certain discrete interval system. There is no question about that. And for example, if you take this Hirota map, why it is called Hirota map? Because if you do this procedure, then you will end up with Hirota bilinear equation.
And same in non-commutative setting.
Yeah, of course. But in non-commutative case, maybe you will have some problems of identifying some minimal set of variables because some part of equations will be simple equations, kind of, I don't know, like, you know, in electrodynamics, we define the vector potential on the basis that F mu is a closed form. Then we are able to define the vector potential. This kind of, to reduce the variables. And this kind of transformations are more complicated in non-commutative case. Sometimes you cannot do that and you have to keep the bigger set of variables. But otherwise, yes, it doesn't matter. Commutative, not commutative, you have the discrete interval system.
Thank you.
Can I ask something related to the connection of these maps with the discrete that Sasha is asking? So there is a method, recent method by Kastakis, Nisporsky, Papageorgiou, Tongas. They show how you go using symmetries of tetrahedron maps, how you go to discrete 3D lattice systems. The question is if you have tried to see the corresponding discrete 3D lattice systems via this approach.
I think Korepanov some years ago was talking about this. So he was saying that you start from some three-dimensional matrix like matrix. But he was telling about like Ising model. You start from
it was
model and then you apply star triangle.
The case of A, B, C, D being matrices in his.
Yeah, this is one thing. No, but another thing, he had a paper, at least archive preprint, where he talked about star triangle in Ising model, for example, and then you apply star triangle transformation locally. And then this he considered as an evolution in third direction. And in this way, he generated integrable system in 3 dimensions. So I would say that this kind of answer to your question, I would say.
I'll check it out. Thank you.
You're welcome.
Okay. I suppose we have to finish. Rinat, thank you very much once again.
Thank you for your attention and
very interesting. Thank you.
Thanks very much.
Oh, excuse me, Rinat. Sorry, maybe last question.
Yes.
We know connection of a Yang-Baxter equation with braid group. If we have solution, we can construct a presentation and so on. Do you know some connection of some group with tetrahedron equation?
I think that people were discussing about knotted surfaces in 4 dimensions. So, I mean, the braid group is behind knot theory, right? Not if we close braids, then we get knots.
Yes,
and
yes.
In that sense, people were discussing tetrahedron solutions in the context of knotted surfaces in 4 dimensions, whatever it is. So, I mean,
exactly.
Okay. Okay, thank you. Thank you.
Thank you all. Bye.
Bye.
Bye bye.
I